Good day, everyone. Today we're gonna look at the mathematics, Euclidean Geometry, question 9 and question 10. We're gonna look at the mathematics, and that is Euclidean Geometry. And first of all, I wanted to say shout out to those that I subscribe to the videos, shout out to those that I like the videos, and shout out to those that they do comment in the comment section below. You also can do so by clicking the like button, clicking the subscribe button, and also comment in the comment section below because it does help me a lot to reach more people like you. Anyway, let's get into it. So the first question here says that complete the statement so that it is true. They say that that is 9.1. They say that angle is subtended by a chord of a circle on the same side of a chord R. Then they say dash dash dash. So now by looking at that one, you can see that 9.1 here angle is subtended by a chord of a circle in the same side of a chord on the same side of a chord R. Now you can see that they are equal because angles that are subtended by the same chord means that they are subtended by the same chord is something like the chord here subtend an angle, and then the same chord subtend another angle, so that that one makes them to become equal. So now the answer here is equal. Then let's look at 9.2. Here is 9.2. Says that 9.2 in the diagram below, ABFE and EFDC are cyclic quadrilateral in two equal circles. Here are the two cyclic quadrilaterals that intercepted E and F. Here is E and F. B, FC, and AEC are straight lines. BD is a common tangent to the circle at B and D, respectively. So EC is equals to CD. Here is EC, and then here is CD. You can see that they show that they are equal. And let angle here, the C angle D, P is equals to X. Here, C angle D, P is equals to X. Then they say here, proof given results that 9.2.1, 9.2.1, here, angle F2 required to prove here that angle F1 is equals to angle F2. Here is angle F1. Here is angle F1. You can see that this is angle F1 and this is angle F2. By interpretation, you can see that angle F1 is equals to angle X. Here is angle X. Here, because of the tan chord theorem, here is angle X, that is CDP, angle CDP, that is X, and angle F1, you can see that they are equal because of the tan chord theorem, because it's facing that side, and here the tan chord theorem. So angle F1 here is equals to X here. Let's firstly say so. Angle F1 is equals to X. Tan chord theorem. Okay, so we did find that angle F1 is equals to X because of the tan chord theorem. And then you can see that since they say that EC is equals to CD, you can see that these are the chords subtended by these are the chords, just the chords that are on this cyclic quadrilateral, so that this means that angle F2 is equals to angle F1. You can simply say that angle F2 is equals to angle F1. Here is angle F2 is equals to angle F1, and because of the equal chords that they subtend equal angles, then equal angles. I'll just use the symbols to represent my reasoning here, and you can see that angle F2 is equal to angle F1 because of the chord EC that subtend that angle, and then chord CD that subtend the angle that is F1, and then the chord EC subtend the angle F2. And previously we said that angle F1 is equal to X here. Then you can simply say that since angle F1 is equals to X, you can see that angle F1 is equals to angle F1 here, then angle F2 is also equals to Fx. So angle F1 here is equals to angle F2. They are both equal to X. I think we did prove that angle F1 is equals to therefore here angle F1 is equals to angle F2. I think we did prove that the first question. So now 9.2.1 9.2.1, let's get into it. 9.2.1 says here, prove giving reasons that ABDC is a cyclic quadrilateral. Looking at this one, ABDC, here is ABDC, proving that it is a quadrilateral, cyclic quadrilateral. I simply advise you to just put the dot lines to represent the cyclic quad that you are proving, that is AB, then DC. Join them all, put the dotted lines here. Here is our cyclic quadrilateral that we are proving that it. Here is our quadrilateral that we are proving here if it's a cyclic quad or not. So now we can see that here, since we say that this one is X and this one is X, and then now recall from the statement that we read, it says that B, F, C, and the AEC are straight lines. So here is a BFC, that is a straight line. So what we can do now is just for us to find the angle that is EFB. Let's try to find first the angle that is EFB. So EFB here, EFB plus F2 is equals to 180, just because these angles, we are told that here it's a straight line. So these angles, adding these two angles, they probably give you 180. So now let's say that EFB plus F2, angle F2 is equals to 180, and say that angles on a straight line. Okay, now since we said that this angle is this angle f2 here is x, let's replace f2 here. Let's replace f2 here with this angle that we said is x. We can just simply say that EFB now, EFB plus x is equals to 180 degrees, and then EFB, let's just transpose angle x here, the variable x to the other side, then we are left with E angle FB, that is equals to 180 degrees minus x. We said so that here these angles are on a straight line. So since we got EFB as our 180 minus x, let's try to find, since we know that here this ABFE, I think they told us, yeah, ABFE here and the EFDC are cyclic quadrilaterals. So let's just find angle A using the properties of the cyclic quadrilateral. That is, since we got EFB here, let's say adding angle A and angle EFB, we can probably sum up to 180. That is opposite angles of a cyclic quadrilateral. We can just say now, since we got our EFB as 180 minus x, and adding 180 this angle EFB also with the angle A here, we probably get 180, and let's do so. That is angle A. We are trying to find angle A now. Angle A plus 180 this minus x is equals to 180, because these angles are opposite angles of a cyclic quad. That is our reasoning. So angle A here, we are trying to find angle A, and we know that EFB is equals to 180 minus x. That is why I put 180 minus x this here. So here it is our cyclic quadrilateral. We are trying to find this angle from this angle. That is angle EFB plus angle A. They give us 180 degrees. And now let's try to find angle A. That is, when we transpose this one to the other side, we are left with the angle A here. That is 180. The 180 on the side, and minus 180 minus x. So now let's distribute negative to the bracket. That is 180 now minus 180 degrees plus x. And then we can see that these one are additive inverses. Then we cancel them out. They give us 0. And then we are left with x here. Then that is our angle A here. Angle A, that is x. We proved that angle A is equals to x. Then we can see that now to our dotted cyclic quad, the one that we are proving, angle x here appears, and this angle x appears, and then angle x here appears. You can see that this one is the exterior angle of a cyclic quadrilateral. So let's say now, since this one is equals to this one, and we know that the exterior angle of a cyclic quadrilateral is the one that says, or the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle of a cyclic quad. So now you can see that angle x here is equal to angle x, so meaning that this one is the cyclic quad, then the converse of the exterior angle of a cyclic quad. That is what we are proving now. So angle, so then therefore A B D ABTC is a cyclic quad. I'll just put here an O, meaning that it's a cyclic. Then say here quad, cyclic quad. So now the reasoning is that this one is the converse exterior angle of a cyclic quad. Cyclic quad. That is our reasoning. So now we are done with 9.2.1. It's 9.2.2. I mean, it's 9.2.2. So now let's look at 9.2.3. It says that here we can prove that BE is parallel to CD. That is BE, here is BE. BE is parallel to CD. They mean like we have to prove that here these are the parallel lines. So looking at this one, we can say that here is angle A, the one that we got on the previous question, that is 9.2.2, and here we can see that since they said here, I think here BD is a common tangent. Hope you all see that. Once they say BD is a common tangent, things that we can expect from the tangent is that is the tan-chord theorem and tan perpendicular to the chord. So now we don't have a center in any of the cyclic quad. So now probably we can get a tan-chord theorem. So now let's check if a tan-chord theorem can work here. We can see that angle A here, the one that we got here, is equals to angle EBD, that is this angle. It is equals to angle X, that is the angle X here, the angle A. You can see that they are equal because of the tan-chord theorem. This one is the tangent. So what we said here is just that here angle EBD is equals to X, or I mean, let's say it's equals to A. It's equals to A first. The angle that we did prove here, that is equals to A, is because of the tan-chord theorem. Tan-chord theorem, just say so. So now we saw that here angle A is equals to X, since we proved that on the previous question, as angle A here is equals to angle X, and also then therefore angle EBD, since they are equal, is also equals to X, and then we can say that they are both equal to x here. So now let's see that if we can get the properties of the parallel lines. We can say that angle B, then angle EBD, the one that is equals to x, is also equals to CDP, the one that is equals to x here. We can also see that the properties of the parallel lines, the one that we use here is that properties of a parallel lines is that they are corresponding to each other. So if they are corresponding with each other, it means that EB is parallel to CD. So we can just say so. Then therefore BE, the one that we had to prove, is parallel to CD because corresponding angles are equal now here. Then we are done with the 9.2.3, and then let's get into 9.2.4. They say here 9.2.4 9.2.4 they say here FC is they say prove given reason that FC is the diameter of a circle FDCE if it is given that EBDC is a rhombus. Yeah, now let's look at what is this one FC. We have to prove that FC is the diameter of this circle quadrilateral. They specified that FDCE, here is FDCE, and then they say we have to prove that this line is the diameter if it is given that EBDC is the rhombus. Here is EBDC. They say that EBDC is a rhombus. So the properties of a rhombus, we have to look at them. Now we can just say that all lines, they are equal to each other. Looking at this one here, the line, all these lines, they are equal to each other. So that is one of the properties of a rhombus. So now let's check if is that favoring us. So firstly, looking at this one, at this cyclic quadrilateral here, that is FDCE, we can see that here angle F, here is angle F. This one, we can see that here is it's X F1. Since angle F is made by angle F1 and angle F2, we can see that X here and this X, we can just to find angle F here, you can just sum up these two X's and they give us F X 2X, I mean. So angle F here is equals to angle F1. That is what I mean. This is what I mean. Angle F1 plus angle F2. You see? So now angle F1 plus angle F2. Since we said here angle F1 on the previous questions, angle F1 is equal to angle X, then we can simply say that X plus X, then it gives us 2X now. That is angle F. Then if we have 2X here, to find angle C, let's firstly find angle C. To to see if it can favor us. Angle C, here is angle C. Let's try to find angle C using the properties of a cyclic quad. It means that angle C, there we can add here angle F with angle C. They probably give us 180. Those are the opposite angles of a cyclic quadrilateral. Hope you all see that. Here is angle C. When you add angle C with the angle F here, they give us 180 because those are the opposite angles of a cyclic quadrilateral. And let's try to add them using angle F and angle C. That is angle C plus angle 2x. We know that angle F here is what we did. You say that angle F is equals to 2x. Then we are replacing angle F here now with 2x. Then we say is equals to 180 minus. Sorry for that. My mind is faster than my handwriting. So now I'm just thinking of transposing that to x to the other side, of which I have to do on the following step. Now we say that these are the opposite angles of a cyclic quad. I hope you all see that. Now we see we can transpose 2x, and we are left with angle C here. The angle that we want is angle C here. Let's try to find angle C. We say that angle C is equal to 180 degrees minus 2x. Yeah, so now here we got angle C as 180 minus 2x. Yeah, angle C is made by angle C1 and angle C2. So here the angle C here is 180 minus 2x. Then let's try to find the angle C1 and angle C2, so that we can find that this angle FDC. If we can find the angle this one, why am I writing an 90 degrees here? Oh, my mind is just too fast today. I don't know, but let's find angle C1 and angle C2 at the same time. Let's say here now, since they said here EBC, if it is given that EBDC is a rhombus, we know that the properties of a rhombus, the angle on this side must be equal to the angle on the other side. So meaning now we can just say that we can just we can just divide the angle C here, the angle C that we got, since angle C is made by angle C1 plus angle C2. So now let's try to find angle C2. Angle C2, if we can just say here, okay, angle C2, here is angle C2. Let's try to find them. This one plus this one, it gives us angle C. So for angle C2, we can just say that angle C2 angle C2 is made by, okay, angle C, that is a 180 minus 2x. We can just divide that with 2. So angle C2 is equals to angle C1. So here angle C2 is equals to angle C1, properties of a rhombus. Then if so, we can just say here angle C2 is equals to 180 degrees minus 2x all over 2. Then it gives us 90 degrees minus x. That is angle C2. Also angle C1 is equals to 90 degrees minus x. So if that is the case, let's try to find this angle FDC. Let's try to find U. Okay, I'm running out of a space. Now let's do like this. Put them aside. Now I said we have to find, we said here angle C2 here is equals to 90 degrees minus x, and angles, and I mean sum of angles of a triangles, that will be our reason. What I'm trying to say is that when we add all of them, they give us 180. They are supplementary angles. So that is what I'm trying to say. So angle, I said, is angle F1, then angle C2, then angle FDC. We're trying to find angle FDC, then plus angle F1. Here it is FDC, then angle F1, then angle C2 here. That is plus angle C2. That is equals to 180. Those are the sum of angles of a triangle. That is our reasoning. So angle FDC, that is FDC, is the one that we're trying to find. Here it is FDC. We're trying to find that angle plus angle F1, it is x, plus angle C2, that is 90 degrees minus x, which is equals to 180. And then we can see that this one is an additive inverse of that one, and we can cancel them out. Then we're left with FDC plus 90 degrees is equals to 180 degrees. And then when we transpose that 90, FDC is equals to 180 degrees minus x this side, and then angle FDC is equals to 90 degrees. Then we got that angle FDC is equals to 90 degrees. That is why on that time I did wrote this one, because if it's a diameter, it means that the center here, there should be a center there if it's a diameter, and then if it's a diameter, it will probably angles in same sec. So now we can just say that FC is then therefore FC is a diameter, that is the converse of angles in same side. Then FC is a diameter, sorry, the bad handwriting. That is FC is a diameter. Then our reasoning is just that converse, that is angles in same circle, angles in same circle, I mean angles in semicircle. Yeah. Then we are done with the 9 point question 9. Let's look at question 10. Okay, now question 10. Here it is, question 10. 10.2. Start with 10.2. That is question 9 this side. 10.2. Question 10. In the diagram below, triangle is an equivalent triangle. PQR is an equilateral triangle inscribed in a circle. V is a point on the circle. QP produced meets RV produced a T. PR and QV intersect at W. PR and QV intercept at W. So now they say at here they say question 10. Question 10. Question 10, 10.2. They say here now we have to prove given reasons as we did last time. Prove given reasons that 10.2.1 are required to prove here that angle W1 is equals to angle RQ. Then that is Cremax. See? So since they said here triangle PQR is an equilateral triangle inscribed in a circle. This is the circle that we can see, that is PQR. Here is the equilateral triangle, and the equilateral triangle I think we have to note that equilateral triangle, it means that the angles, they are all equal to 60 degrees. PQR, they are all equals to 60 degrees. So now if you can just name that as it is said there, if you can just recall that equilateral triangle, all the angles are just equal to 90 degrees. So now let's try to prove that W1 is equals to T angle RQ. That is T angle RQ. And we can see that that one is angle R, if you can say so. This angle here, we have to prove that it is equal to this angle. Okay, now if you can take a look at this one, you can see that WVR, this triangle here, WVR here, angle W1 is an exterior angle of a triangle WVR. So if it's an exterior angle of this triangle, it means that it has to be equal to angle WVR, this angle here, and then R2 here. It has to be equal to them because the properties of an exterior angle of a triangle, it means that it is equal to two opposite interior angles of a triangle, of that triangle. So it has to be equal to R2 and this angle here. And to find this angle, we can see that since it's a cyclic quadrilateral, we can see that angle 60 here, the angle that is P1, is equals to this angle because of the angles in same sec. I hope you all see that angle 60 that is here is equals to this angle that is WVR, angle WVR, because of the angles in same sec. Okay, now to see the angles that are in same sec, that is the segment that we are talking about, that is QR. It subtend the 60 degrees, and then also this same segment subtend also the angle that is there, that the QVR. Then if it's so, definitely this angle is equals to this angle. So let's see that how we're gonna get W1 equals to angle R. So now, since we got an angle that is equals to the one that is the 60 degrees, we can say that here is 60 degrees because of the angles that are in same sec. The segment that we're talking about is QR. So now let's try to say so. Let's show that first of all, angle P1 is equals to W angle VR. That is angles in same sec. So now if this angle is equals to that angle, and then let's try to find also angle R2. Okay, now to find angle R2, it will be a bit difficult. So let's try to use a letter here, maybe a variable that is x here. Let's say so, angle R2 to be x. So now let's try to maybe let me first say that the angle W1 is equals to angle WVR. Here is this angle WVR, the one that I said so, plus angle R2, I mean. Then we say their exterior angle of a triangle. Exterior angle of a triangle. And now since this one is equals to that one, angle R here, angle R here is equals to angle R1 plus angle R2. You see, here is angle R, the angle R, the whole angle here it is angle R, is equals to angle R1 and angle R2. So if it's so, it's just there's no reason, but you can see that it's equal. It's equal. So angle R, we can see that here, to make it short, we can see that angle R2 appears here and angle R2 appears there. So at first I said that angle R1 is equals to 60 because of equilateral triangle that they mentioned there, and then angle WVR is equals to 60 degrees also. And then let's say W1 is equals to 60 degrees plus angle R2 here, and then angle R also is equals to 60 degrees plus angle R2. So let's try to say, since we can see that the angle R here is the one that they said we have to prove that T angle RQ is equals to angle W1. So you can see that here we got angle W1, and then we have angle T angle RQ here. So these one are the ones that we want to find. So let's try to make a R2 a subject of the formula here, and say angle W1 minus 60 degrees is equals to angle R2. So let's try to put here to replace angle R2 with angle W1 minus 60, and we can get that angle R, I mean it's angle R here, angle R is equals to 60 degrees plus, then in brackets W1 minus 60 degrees, and then we get an additive inverse here, 60 and 60, we can just cancel them out, and we are left with angle R is equals to angle W1. And I think I said so that angle R here is the one that it is T, R, and Q. So if it's T angle R, Q is equals to W1. So I think we did prove that they are equal. Okay, we can just say, then therefore the T angle RQ is equals to angle W1. Then we are done with 10.21. Then let's try to get into to look at 10.22. Yeah, now here is 10.22. 10.22. They say here we have to prove, given reasons, that angle TQR is similar to angle QRW. Let's try to look on that one. Triangle TQR is similar to triangle QRW. So triangle that is TQR and QRW, that is TQR and also and QRW. Okay, now we have to prove those that they are equal. So now we can just say here triangle TQR and triangle QRW. We have to prove them. We are required to prove this one. They are similar to each other. So proving them out, let's say we have T here and then we have Q here. Let's see the relationship, that is Q T here and Q on the small triangle here. That is T from the big triangle and then Q2 from the small triangle. We can see that there is for now there is no relationship since we didn't prove anything related to T and Q2. And then let's check this one, Q here, Q and R here. We can see that Q, I think it's the Q, the big Q, Q and R. I think it's here it's R, small r. Oh, okay. So now, if you can recall now, it's just that Q from the big triangle and then Q and then R1 from the small triangle. Then we can see the relationship here. It's just that we were told that this one is an equilateral triangle, and then definitely angle Q here is equals to angle R1. They are both equal to 60 degrees. So here for the one, we can say that angle Q is equals to angle R1, given that here is an equilateral triangle and then they are both equal to 60 degrees. That is our reasoning given here. That is given. So for the second one, let's try to find for the second one, R here, R from the bigger triangle, and then W1 from the smaller triangle. That is the R from the bigger triangle, and then W from the smaller triangle. Then definitely that is the one that we proved above, that W1 is equals to T angle RQ, if you can remember that. So now we can just say angle R here is the R from the bigger triangle is equals to angle W1 from the smaller triangle, and then we can just say proven above. If it's proven above, it's just the reasoning for this one, since we did prove on 10.21. So now let's try to find the third angle here, that is T from the bigger triangle and Q2 from the smaller triangle. The one that we said there was no relationship, any clue that was given from the statement. I hope we all see that that there was no clue, of which we know that if this angle is equals to this angle big R is equals to this angle, and then this angle is equals to this angle, then definitely it says that Q2 is equals to this angle, because it's the third angle of a triangle. You see, so that is our reasoning here. So now we say Q2 that with T, angle T is equals to angle Q2 from the smaller triangle, and then we can just say that it's a third angle of a triangle. So now, since we got all our angles equal to each other, we can just say that then therefore delta, or I mean triangle TQR is similar to triangle QRW because of the angle. That is the property that we use for similarity. And then let's get into 10.2.3. It says here, we are required to prove what PT over QW is equal to PV over WR. 6 marks. Worth is 6 marks. Wow, we're gonna work here. I promise you guys, we're gonna definitely work. Okay, so now 10.2.2, 10.2.3, it says required to prove that PT over QW is equals to PV over WR. So I want you guys to take a little thing that I usually use when I see that there was nothing that I did on the previous question that can definitely help me to come up with these 6 marks. I usually say here, since I don't find anything here that is related to PT, QR, or PV, WR, or here it is QW. You see, so I usually say to myself, okay, let me try to find a triangle here connecting these terms. The letters, connect combining them all together to give me a triangle that can probably give me a similar triangle. Okay, now let's try to say. Okay, now let's try to combine all of them and say PTV. Here it is PTV. Let's try to find a triangle PTV. Here it is the triangle PTV that I'm combining the letters for to produce a triangle from this that they do say I should prove given reasons from, and then I say QWR. So now is QWR this smaller triangle. Let's try to find a way to prove a similar triangles here, and then we will see if it gives us exactly the letters, this thing, PT over QW is equals to PV over WR. Okay, now let's say for triangle PTV and triangle QWR. Okay, now let's say for these triangles, let's try to find the similarities, similar triangles from them. So now let's say, okay, maybe let's say yeah, okay, let's look at them. PTV. Okay, let's try to find let's try to find angles that we proved above, and then they gave us something like if you are looking at P and Q here, P here, P, that is P2, and Q here, that is Q2. There's no relationship. T here, it is T, and then let's try to T and then W. No relationship. T and W, V and R, V and R here. Also, there's no relationship. R1 and V1. Also, there's no relationship. Let's try to find. Let's try to maybe arrange these terms, these letters, and say what is P here. It's P. Okay, or maybe let's try to since. Okay, now we can see that P2 is equals to angle R here. So okay, now we were trying to combine these letters in such a way that they give us a similar triangle. So I said here is P, here is P now, P2, here is P2, then we can see that P here is the exterior angle of a cyclic quad. Then definitely it is equal to angle R, the angle R for the cyclic quad. And then we know that angle R here is equals to angle W1. So if so, we can simply say that here I said we can simply say that here okay, I said we can simply say that these triangles, arranging them according to the combination that they give us a similar triangles P, P, and then this side is a triangle W, and then T here. Let's try to find a combination for T. Anyway, we said here on this one, the third angle of a triangle, we said here angle T is equals to angle Q1. Okay, now we get into something that is PT, and then here we say angle Q. Okay, we leave it like that, and then we are left with the V and R. So most definitely those one they are probably equal as the third angle of a triangle, as we did TV, then WQR. That is the that is the best combination now that can give us similar triangles. So now here we can just simple do the similarity, prove the similarity for this one. We say that here angle P2 is equals to angle R, exterior angle. We can just show that for now, exterior angle of a cyclic quad. So now P2 is equals to angle R, and then we know that angle R is equals to angle W1. So definitely P2 is equals to angle W1, both equals to angle R. Then we get our first angle that is equals to each other. Then for the second one, we can look at T and Q. We can see that angle T is equals to angle Q2, since proven above, since we did prove it as the third angle of a triangle, proven above. Then now we can say here V, the third angle now, angle V here is equals to angle R, or let's check here if it's angle R. Yeah, it's angle R1, and then now it's V1, and then angle R1 here, okay? Angle V1 and angle R1 is equal to as the third angle of a triangle. I think I did discuss with you that the third angle of a triangle, they are equal because the two angles are equal, and when you subtract them into 180, they probably give you the same angles. So now, okay, let's definitely say that let's say here triangle PTV is similar to triangle WQR because of the angle. You see, hope you all see that. Since we proved that these are the similar triangles, let's try to find a combination in such a way that they give us the one that they asked in the question. So I'm running out of space here. Now I remove. Okay, now here they say it here is PT over QW, which is equals to PV over WR. Okay, from our similar triangles, we know that PT over W, PT over Q over WQ. Okay, let's write that down. We say that here is PT from our similar triangles. PT over QW is equals to, and now is TV. We'll write them all. TV over QR, which is equals to a PV now over a WR. We got them on the similar triangles. Similar triangles proven. You see. So now that is our reasoning. Let's check if from these we get PT over QW, PV over here it's R. We get PV over WR. Okay, we can simply see that this one they give us the exact as it is asked on the question. So now we simply say that PT over QW is equals to PV over WR. I hope we all see that. Then therefore, you see, I hope we all see that as it is asked on the question here. That PT over QW, here is PT over QW, and then PV over WR. All right, that's it for this video. Thanks for watching. Anyway, me and you, we're gonna meet in the next video. But until the next video, please guys, do take care. Don't forget to subscribe, to like the video, and also to comment in the comment section below. That's it.